Now we're able to go and use sum and difference identities now that they've been derived and they've been proven. So we're going to skim on down since I've already done that proof in a different slide. How are we supposed to use and evaluate a trigonometric function by finding the exact value of each trig expression? So what it's going to do is it's going to expand the number of trig values or angles that we can find exact trig values for. So we're supposed to use our sum and difference identities to come up with some connections to finding other cosine and sine of angles. So 15 degrees. What we got to be doing is thinking of the angles that we do know exact values of. And what I said the other day is you really want to be thinking of your 30 degrees, your 45 degree, your 60 degree, and then all of your quadrantial angles, such as 90, 180, and 270. And I suppose 360 could come into play as well. But what you want to do is say, what kind of combinations could I use either as a sum or a difference to end up with the angles that we have in front of us. In this case, it's the cosine of 15. The cosine of 15 isn't too rough on us. It's not too hard of a value to come up with. I'm sorry, I'm just trying to reposition these and get them all at once. There we go. And just a little managing here. Okay, we're all set up. So what we said we were going to do, and we did this the other day, is we went, this is the cosine of 15. The cosine of a 15-degree angle could be thought of as the cosine of, if we use our angles of 45 and 30, and we subtract them. So 45 minus 30, that's a 15-degree angle. So now we can apply our cosine of a difference identity. So that says you take the cosine of the first angle times the cosine of the second angle, and then you add to it the sine of the first angle and the sine of the second angle. So a 45-degree angle, the cosine of a 45 is the square root of 2 over 2. The sine of a 45 is square root of 2 over 2. 45, the sine and cosine values are the same. 1 over square root of 2, and I rationalize. Then I also want a 30-degree angle, so I'm just going to do a quick representation of a 30-degree reference angle. So if this is 30, this side is 1, this is 2, this is your square root of 3. If we do the cosine, it's the square root of 3 over 2. So you're going to multiply those together, add it to the sine of a 30, which is the 1 over 2. And multiply those two together. So we do a little simplification here. We've got the square root of 6 all over 4 plus the square root of 2 over 4. And like we mentioned, it's the square root of 6 plus the square root of 4 over the, the square root of 2 over 4. Now this is the exact trig value for the cosine of a 15-degree angle. So I want to store that one over here just a little bit. And again, I wish I could grab the whole thing, so let's see if I can grab it all. And I'm going to store that over here, right next to it, up here. And then I'm going to clear out a lot of workspace here so I can do the second one. The second one is in radians, and I'd like to see you stay in radians and not change it or convert it right away back into degrees. But you know, every method has its pluses and minuses. If you want to change it right back into degrees, you can. In this problem, it would work really well. Here's what I want to try to drive home the point with on these. This should be the sum and difference of some known angles that we already know, such as pi thirds, pi fourths, pi sixths, and again, you can go into your pi halves and pi and 3 pi halves and use those if you need to, and then, of course, 2 pi. But since this is in 12ths, I'd like to see all these fractions in a common denominator. If I don't see the connection right away, so what I can do is I can write pi 6 as 2 pi 12ths, and I can write pi thirds as, that's 4 pi 12ths, and I can write pi fourths as 3 pi 12ths, and so on. And until I find a connection, so pi halves is 6 pi 12ths. But I'm going to stop at that because at this point I can see that I could use a sum identity to combine pi fourths and pi sixths, because that's a 2 pi 12ths plus a 3 pi 12ths, which would be a 5 pi 12ths. So this is going to be written as the sine of a sum of pi 6 plus pi fourths. Then we will apply our sine of a sum identity. Now the sine of a sum identity says you take the sine of the first angle, which is the sine of pi 6, I'm going to get rid of that parenthesis, so sine pi 6 times the cosine of the second angle, which is pi fourths, plus the cosine of the first angle, which is pi 6, and times the sine of the second angle, which is pi fourths. Okay, so sine of the first, cosine of the second, cosine of the first, sine of the second. Just talking myself through that. Now, pi 6, again, is a 30-degree reference angle, so we've got a 1, 2, square root of 3. So the sine of that is a half. We got to take it times the cosine of the pi fourths, which is 45, square root of 2 over 2, plus the cosine of pi 6 is the square root of 3 over 2, times the square root of 2 over 2. And this will give us the square root of 2 over 4, plus the square root of 6 over 4. And again, we can write that over a common denominator, or just one denominator, 4. And the reason I wanted these two to stay up here is because these two are exactly the same, and I want to highlight one more connection here. That if you have a 15-degree angle, a 15-degree angle is related to a 30-degree angle. So I'm going to come back and make this a 30-degree angle. 15 is half of 30, so therefore what I want to think of 30 degrees is pi 6. So then half of a pi 6 is pi 12. So anytime you see a 15 or a multiple of 15, it's really a multiple of pi 12s. And what we had was 5 pi 12. So if we had 5 of these, and if we multiply this times 5, and multiply this times 5, it would be a 75-degree angle, and this is 5 pi 12s. And the connection I was trying to make is that if this is a 75-degree angle, and this is a 15-degree angle, and you think about complementary angles, that if one angle is 15, then the complementary angle has to be 75. And what we said, and the complementary angle can be here as well, is that the sine of a cosine of a 15-degree angle has to be the exact same as the sine of the other angle in your right triangle, which is 75. So that's why they ended up being exactly the same. They were complementary angles, which means the cofunctions of those complementary angles would have to be identical. So enough with question 1.